All right, so this is part 2 of the review. And we were on problem number 11. And I wanted to know the end behavior of this, right? So we were doing I'll also try to share these notes with you. I haven't done that in forever. But I can put the links online and share the pages with you as well. Although I'm all over the place when I'm writing. And so we have the table again, right, that says that we are looking for the degree and the leading coefficient. And so just by investigating this, how are you? The degree is, in this case, the degree is just add the powers. I think this thing's finally working now. Add the powers. Looks like the degree is 6, which is even. Everything looks positive in terms of the leading coefficient. It looks like it's 1, which is greater than 0. And so even degree, leading coefficient is positive. Table, wherever your table is, says that it rises to the left and it rises to the right. We just want to express that in calculus terms. That means that as x goes to minus infinity, then let's put this in. That means as x goes to minus infinity, the function should go to infinity, and if x goes to infinity, the function should go to infinity. It rises on both sides. Even degree, positive coefficient. Yeah. Questions on that? Yeah, we may roll through these, right? 12. Oh, here's where it gets fun. Here's a polynomial, degree 4. Oh, let's try and do this now. Okay, so pick a polynomial. Pick a poly. Okay. Polynomial has degree 4, has a root of multiplicity 2 at x equals 4, and roots, I actually just need to make this smaller. That's too small, right? Can we see that? Yes? No? Okay. Polynomial of degree 4, p of x has a root of multiplicity 2 at x equals 4 and roots of multiplicity 1 at 0 and negative 1. It goes to the point 5, 9. Right? So I just reintroduced a bunch of mathematical jargon to you about this. It says, so here are some comments I want to make about this. Here's the street version. That, well, this is still mathematical. Polynomials are just products of linear factors. It's x minus 1 times x plus 5 times x minus 3 times x plus 2i times x minus 2i, right? They're just products of linear factors. So here we're just saying I need x minus this times x plus that times x minus this times x plus that, right? Because it's degree 4. So I need 4 terms, right? Here. 2 of them are going to repeat. The one with what? Which one repeats?
4.
4 for sure, right? So we're talking about x minus 4 times x minus 4 times x minus 0 times x plus 1. That's what we're talking about, okay? And when you multiply out, that will be a polynomial, but they don't even need you to multiply it out, right? So if we're talking about x minus 4 times x minus 4 times x plus 1, right? And now we just need to make that go through the 0.59, right? And so when we translate this super carefully, we're talking about highest power. So you need 4 linear terms. Right? That's what this 4 is for, right? And then we're talking about x minus 4 squared times x minus 0 times x plus 1. If I have written this nicely. Yep, I have. All right, so we're talking about x, we're talking about x times x plus 1 times x minus 4 squared. Okay. Brother, good morning. And so that alone satisfies all of the roots. I don't need you now. Right? So now we have to satisfy one more condition, as that it goes to the 0.59, and therefore that means there's one more parameter. Oh, I'm going to use a different letter, different color. There's one more parameter here, lambda, or I should say omega, right, that we need to pick so that this final condition is satisfied. This is a function. And when I plug in 5 in for x, I need to get 9. Right? So f of 5 equals 9. And so then plug in 5, set equal to 9, solve for that final number. Okay. 9 equals the thing we're looking for times 5 times 6 times, we're plugging in 5, right? 1 squared. 9 equals 30 omega. Omega is 9 over 30, which reduces to 3 over 10. And that's the game. 3 over 10 times x plus 1 times x minus 4 squared. Any questions about that? Let's see if that works out. 3 over 10. 3 over 10 times, let's do this, x, parentheses, x minus 1, parentheses, x plus, x minus 4 squared, right? Mm-hmm. No, it's x plus 1, right?
It is x plus 1.
And then x minus 4 squared. Let's see if it likes that. Okay. Great, great, great. 13. What in the hell is that?
Couldn't tell you.
Yeah. Oh, well, you will by the 31st. That's right. When this is due. That's right. So, this is a polynomial, okay? It could be of however many degrees because we don't see the rest of the graph, but we can give one guess as to what it is just based on what we see here, right? The remark is that for a mathematician, this function, this problem and the previous problem are exactly the same. We've just given you the graph instead, okay? So what are the zeros? -1 and 1, okay? So here is where it gets kind of funky. Way too big. Okay. Okay. So it looks like we have what's going on here. Right, so let's look at the zeros. So let's write this in steps. So let's get the zeros first. So the zeros are -1. What else? 1. Anything else?
3. Are we also including the y-intercept?
Nope, just where it hits the x-axis. Is that it?
That's it.
Okay, very good. Okay, so now, I need an x plus 1, and I need an x minus 1. Okay. And the question is that enough to make this? Right? Why is this wrong? Very skeptical will come in and say, this can't be right, because look at -1. What happens at -1? It turns. So that the power on x plus 1 needs to be
Squared.
it needs to be even. That's right. It needs to be even. I'm going to take a question on that.
That's it?
And then at 1, what happens at 1? It crosses, right? But it looks weird at 1. It doesn't cross like a regular.
So it's odd?
It is odd.
Oh,
And it's more than 1. Yes, it's more than 1. We're going to try 3. I didn't take any questions on why it's more than 1. If it's more than 1, it goes through like a line, right? Because it's linear, right? So, yeah, we'll try 3. And then, of course, there's one more hidden assumption that we have here, and that for some reason at 0 it's 3. So there's omega again. Here's the function, and at 0 I need it to be 3. F of 0 is 3. Okay. And so when I plug in 0, I better get 3. So 3 needs to be equal to omega times 0 plus 1 squared times 0 minus 1 cubed. 3 is equal to omega times -1. Omega is -3. The function we're talking about might be -3 times x plus 1 squared times x minus 1 to the third. Okay. Now, you'll get something like this at this very problem on the test, and you'll need to see whether it's right. It would be nice if you just went ahead to Desmos and graphed it, see if it matches, right? But one of the things that we've been practicing is to be able, again, the genius of our predecessors, to be able to make sense of this without having to look at the graph. So obviously, we are in a place now, it's the greatest time, it's a great time to be alive, right? Where not only do we have all the knowledge of our predecessors to do stuff intuitively and understand it, we have the technology to verify all of it. And therefore, the best of us can do both things, right? That we should not only be so ancient as to say, well, we're never going to use don't use any calculators in your class, right? I still have liberal arts colleges all over the nation that in Calc 1 and in all these math classes, no calculators. It's a crutch. You don't, you need to think, right? So no calculators at all, no Desmos ever, right? I have some other people who just like, yeah, crutch, do your calculator, use your calculator, you don't need to think about that, use your calculator, right? Both of those are wrong, right? We have to be able to say, okay, this makes sense because this, right? But just in case I might be wrong, let me go and program this right now, right? Think about being able to do both of those things. That's super impressive. We get this, and so let's reason why this might be right. And one of the ways we can do it is the end behavior. Right? What's the degree of this polynomial?
Right now it's 5.
Right now it's 5, right? So it's odd. What's our leading coefficient? It's negative 3, that's right. I guess you couldn't put negative. Well, I guess you could do this. So, that's right. Negative 3, that's right. And so the table, does that fit the table? Odd degree, negative coefficient, right? If it's odd degree and positive coefficient, it would fall to the left and rise to the right. I got a negative coefficient, and it should rise to the left and fall to the right. So that at least fits that according to the end behavior, right? So, yeah. So without even looking at Desmos, you can reason that, okay, this might be okay because of the end behavior, right? Let's go ahead and put it in. But people are writing now, so I'll leave this up for just a second. As I mentioned before, part 1 of this review that I recorded last week is in my Open Math at the beginning of the chapter. If you go into chapter 3, it's at the top. I could not put it right next to the chapter review, so it's just at the top. And so this recording will be right under that as well. Negative 3 times x plus 1 squared times x minus 1 cubed. X would be nice. X plus 1 squared times x minus 1 cubed. Let's see who likes that. Questions? Just breaking it down in terms of the zeros. In behavior, we said this is another table for this one. We have rational functions, right? And this takes care of all the possibilities. So again, as you're getting ready for this, get organized, have your table ready. And so again, way too big. This is about when the powers are the same, different. Right, so they're asking for the long-term behavior. In other words, let's write all the ways this could be said. So they want to know what are the y asymptotes, right? Okay. So rational functions, this is about comparing the highest power in the numerator to the highest power in the denominator, math-wise. It's about the degree of the numerator versus the degree of the denominator. When the powers are the same, you just take the ratio of the coefficients. So this here would be like 1 over 1 for sure. So I should use black so I can see the marker. So that's just 1 over 1. This should go towards the line y equals 1. I can't wait to see how they write these as answer choices. But when the power in the denominator is higher, it's y equals 0 is the horizontal asymptote, and when the power in the numerator is higher, there is no horizontal asymptote. So we might want to say more. I'll see what the answer is that we're talking about. So if there's no horizontal asymptote, that means that this thing is either going to go to infinity or minus infinity, and because of the signs here, everything here is positive. As x gets larger and larger, it should go to plus infinity. But we'll see. Well, let's see what the answer choices are saying. So this says there's no horizontal asymptote. Okay, good. This is no horizontal asymptote. This one says there's a horizontal asymptote at y equals 0, and this one is obviously there's a horizontal asymptote at y equals 1. Super straightforward, right? Just according to the powers.
Can we go into the notes page real quick?
To where? Oh yeah, sure. Yeah.
Oh.
Yeah, I've written nothing. Yeah, so it's just about the table. Do you want to write this table again?
If we could.
Yeah, sure. So when the powers are equal,
No, I guess I have one.
I believe you do. The coefficients, so it's the ratio of the coefficients. Ratio of coefficients. That is the third problem presented here, where you have the powers are equal. I'm always losing this marker. Where the powers are equal here, and it's just 1, this coefficient over that coefficient, right? And again, if this was a 7 and that was a 5, the answer would be y equals 7 over 5. Here, whenever the powers, regardless of the coefficient, whenever the power in the denominator is higher than the power in the numerator, then this thing's going to vanish the larger you make x, right? So it should go to y equals 0. Okay. If you flip it, right, and the power in the numerator is higher, then this is not going to level off at all because the numerator is going to be like, I'm getting so big and you can't bring me down. X squared, you're just not powerful enough to bring me back down. So I'm not going to level off at all. Questions there? Sweet. $15. Yeah, excellent. 15 asks the whole gamut. 15, one of the, in quotes, harder problems, only because now we're faced with factoring. So the y-intercept, we know how to do all of this stuff. The y-intercept, set x equal to 0 and solve and see what you get. So we'll set x equal to 0. Right. So you get 2 times 0 squared minus 1 times 0 minus 10 all over 2 times 0 squared minus 11 times 0 over plus 5. Nothing survives in the numerator but negative 10 in the denominator, 5. So they probably want the point 0, comma negative 2. We'll try and enter it in that way, see if it likes it. Y-intercept is what happens when x is 0. The x-intercept is where this function is equal to 0. And so that means you want this fraction equal to 0. The only way a fraction can be equal to 0 is if the numerator is 0. So you're just taking the numerator, setting it equal to 0, and solving. Oh. Set the numerator equal to 0 and solve. So we're talking about 2x squared minus x minus 10 is equal to 0, and here's, you just got to factor. You got to try stuff out. 2x, x, minus 5, plus 2. So you need to put the factors of 10 in the right place so that when you multiply one of them by 2 and the other one by negative 5 and you add, you get negative 1 in the middle. Right, so yeah, you just play around until you get the one that works. You put this in the Desmos, it's actually not going to be so bad because it'll tell you 2.5, comma negative 2. The only problem is when like the answer is 7 over 3 and then Desmos gives you a decimal and you don't know what that decimal is. Right, you're just like, you don't know what fraction that decimal is, right? But here's one of the nice cases where if you aren't able to factor this, there are other ways using technology to find out what the zeros are. So then you would set each one equal to 0 and solve. 2x minus 5 equal to 0, x plus 2 equal to 0, x is 5 over 2, and x is negative 2. So it looks like we're going to put in it should probably take 2.5 comma 0 and then a comma negative 2 comma 0 like that, right? Assuming the denominator isn't crazy. The denominator might be crazy here. Let's see here. We got to make sure that nothing cancels out like this. 2x x minus 5, x minus 1. Okay, so that's good, right? So there's no crazy things going on. So yeah, you have to factor the denominator and set that equal to 0. So it's more factoring.
What are we doing, the vertical?
That's right. For 3, it's vertical asymptotes. Yeah. And so it looks like x equals 1/2. Oh, I guess it's just 1/2 comma 5. So you set 2x minus 1 equal to 0. And you set x minus 5 equal to 0. And that's where you get 1/2 comma 5. Add 1 and divide by 2. And then you just add 5 on both sides. Right, so it's just going to be how, for this one, it's just going to be how funky the factoring is. But the result remains the same. The idea remains the same. Set the numerator equal to 0 for the x-intercepts. Set the denominator equal to 0 for the vertical asymptotes. What's the horizontal asymptote? Powers are the same. Y equals 2 over 2, 1. Are equal. Right. We'll roll through all of that. The only thing I wanted to check was really, what is that, 0 comma negative 2, right? 0 comma negative 2. I wanted to check these because now here you just separate with a comma, right? So we got 2.5 comma 0. Let's see if it takes the decimal. And then I should separate that point with a comma, right? And then what was the other one?
Negative 2.
Negative 2 comma 0. Right. And then here we should just be able to separate this with a comma. And then the other one was 5. And then y equals 1. Right. Let's see if it likes these. Okay. Good. Rational function with those properties. Rational function with these properties. So that means get the fraction bar together. So to be super clear, a rational function is the ratio. It's not just a function with a fraction bar. It is the ratio of polynomials so that the numerator and denominator are both polynomials. Okay. So we'll do some translating now. Let's put this in red. I haven't seen it in red in a while. Beautiful. So this means that vertical asymptotes, this means that in the denominator you need an x plus 6 and an x minus 4 in the denominator, right, at least. And here in the numerator you need an x minus 5 times an x plus 2. Those two linear factors makes the numerator equal to 0. And then you need a horizontal asymptote of 10. That means that looking at your numerator and denominator, it looks like both of the powers are equal. But now you need to make sure that the ratio of the coefficients is 10. This has infinitely many answers, but we're probably going to write the simplest one. Here, this is one of the rare ones where I don't think the answer is unique. So here, as it stands, what is the horizontal asymptote of this one? The one that I've written so far. It's 1, right? So the highest power of the numerator is 2, highest power of the denominator is 2. The coefficients are just 1 over 1. How would I fix this and make it 10? Just put a 10 there. That ends it. Just put a 10 out front. I could put a 10 with the x inside and a 2 with the x inside the other one. I could write all sorts of funky things. I'm dying to know whether the programmer had all that planned. But this is the simplest way of doing it, right? So just stick a 10 out there. Super straightforward, I hope. It's the ratio of x minus 5. Ooh, yeah, that's right. Oh, I'm not happy with this. X plus 2. Yeah, that's why I'm not happy with this. Let's go back and put this here. I need all that in the numerator. And then the preview again is the greatest thing ever. X minus 4. And then, as we said before, I could just put the 10 there, right? Let's see if it likes that. It doesn't like it. I'm going to be super mad if it lets me put the 10 on the outside. Right? So, hopefully I've written something wrong. Let's try that. Good. It's consistent. Where's the error? Where's the mistake?
Oh, there's a parentheses that doesn't get.
Oh, good. I need one more here. Is it really that? Oh, it didn't give me the preview. No, but wait. It told me it was that, right? Oh, but it didn't tell me. It just told me it didn't like it.
There you go.
Oh, okay, so good. I got 2 more chances.
Okay.
Now it's okay. So let's put the 10 back in here. Still doesn't like it.
Careful, you're only getting a 9.6 from the grade book.
I know. This is attempt 4, right?
Yeah.
Syntax is okay, right?
Yeah.
Oh, that's bad, right? So, but it's okay. So leave the 10 on the outside. Okay. So yeah. So the grader, the programmer wants you to, yeah.
Even though technically it shouldn't make a difference.
No, because the leading coefficient is still 10. When you FOIL it out, it's still going to be 10 over 1, right? But the programmer for sure just wants you to leave the 10 on the outside. There's also something funky going on. So it looks like you lose 20% every time you get one wrong. So I'm going to change that on the test.
Well, it's after attempt 2 you start losing points.
After what?
So like
After 2 attempts?
after 2 attempts, if you get both of those wrong, it'll still be 10, like 10 points if you get. So if you got it right in your second attempt,
Oh,
it's
okay.
2 points.
That's interesting.
But if you get it wrong in your third attempt, it would only be a 9.8,
I did not know that.
and then it
Okay.
would be 9.6.
Okay.
And then it's your fifth. You can't try again.
Okay. Okay. What's that one? What's the graph of that? Let's see. So we got some vertical asymptotes. Same question we just answered, except now we're just given the picture, right? So we're going to be asking, where are the zeros and where are the vertical asymptotes, right? So zeros and vertical asymptotes, right? Okay, so we're talking about the zeros. Looks like, oh, looks like there's only one. Yeah, it looks like it's only one. So x minus 1, right? Vertical asymptotes at
X plus 2.
x plus 2, x minus 3. I just need some, let me call it a different. Oh, that's weird. Did it actually go to another class? I guess I did. That is geometry. That's what's great about teaching this class. Just teaching everything and seeing like all sorts of subjects. It's a lot of fun. I need omega so that at 0 I get 2. So here's f of x. At 0, you're 2. So 2 is equal to omega times 0 minus 1 over 0 plus 2 times 0 minus 3. Omega, 2 equals negative omega over negative 6. Omega is 12. Negative 12 equals negative omega. Omega is 12. the function we're talking about is 12 times x minus 1 over x plus 2 times x minus 3. What?
Program, I tried that, did some weird ones, like it would have like, I don't know, 12 times x as omega, and like
That's interesting. I'd like to take a
it
look.
took out an x on the outside for a lot of their answers.
Okay,
to
I would like to
x
see that.
as,
Okay.
like, as omega. I don't know.
Okay. No, that's, yeah, please, yeah, we'll talk about that. 12x. X minus 1 divided by, and then x plus 2 x minus 3. So it likes that. It doesn't like that. My calculation is wrong, you think?
Should we go back page?
We should. I just want to make sure that's x plus 2, x minus 3. X minus
So what
1.
they need to be, do we need to test some values to see if there needs to be a negative in front of them?
Yeah, so the sign might be right. So 0, x minus 1, x plus 2, x minus 3. It's x minus 3, right? X plus 2. That looks dead on right? 12. We could check. As you go from 3 from the right, no, that is wrong. So we do have a sign error. Where is it? Three from the right, you're supposed to be negative, but that's not true. It's supposed to be negative 12, but where is this sign issue coming from? At 0 is supposed to be, oh my goodness, that might be 1 minus x and not x minus 1. But it should still come out. The sign should come out negative if it's supposed to be negative. Yeah, so x minus 1, x plus 2, x minus 3. Takes care of the whole thing. You plug in 0, you're supposed to get 2. 0 minus 1, 0 plus 2, 0 minus 3. Negative w over have a look. I don't see it. I don't see it. Why the sign is off? I need another pair of eyes for sure.
So, like, if you plug in like 2.99 or something.
No, that's why we knew it was wrong. Oh my God. Okay, so yeah, at 3 there's a problem in the sense that that should be that one needs to be squared.
Oh, because it approaches twice.
It approaches the same way on both sides. Yeah, it approaches the same way on both sides. So so if we change that to a square, then things are very different. So that should be squared. And so the reason is that on this side and on this side, the sign is the same. The sign is the same. And so that means that it has to be of even degree. And so that changes the whole thing, because then that squared And then that means that is not 6. That is not, that's 18. That is 36. And W omega is negative 36.
What is that? Let me just get this.
No worries. Omega is negative 36. All right, so that is the funky revelation. Negative 36 times x minus 1 over x plus 2 times x minus 3 squared. That's fine. Right, so whenever you're approaching an asymptote and it's going the same direction, then the degree of that linear factor has to be even. Yeah. So that fits. That should fit.
Can you say that one more time?
Yeah, so when you're approaching an asymptote and on both sides of the asymptote you're either getting plus infinity or minus infinity on both sides, then that means that the degree of the term where the asymptote is has to be even. They don't have opposite signs. Let's try it now. That's subtle. That is a serious, that's a college question. That's good. Six. Let's see if it likes this. Alright, we're gonna learn something else. See if it likes that. Yeah. Excellent, excellent, excellent. 18. What's the inverse? We're going to set y equal to that thing. Solve for x. Switch the x's and y's. We're semi-experts at this. Inverse. Get into the habit. Roll through this one. Y equals three plus the square root of 3 minus x. Beat me to the answer. Solve, number one, solve for x. Y minus 3 equals the square root of 3x minus 9. Square both sides. Y minus 3 squared equals 3x minus 9. Add 9 to both sides. Y minus 3 squared plus 9 equals 3x. X equals y minus 3 squared plus 9 over 3. Switch the x's and y's. Right, the inverse is x minus 3 squared plus 9 over 3. Rectify any of those steps. Subtract 3, square both sides, add 9, divide by 3. Just completely unraveling what the original function was doing. Any function that completely unravels this function, that's the inverse. That's what the inverse does.
Can we go back to the last page really quick?
Oh, sure. This page here?
Was it this one? It was this one.
Yeah. So yeah, we got again, yeah, we made the remark that the term for 3 needed to be even.
Thank you.
Yeah. Perfect, perfect, perfect. Okay. Okay. 19. Same thing. solve for. I may take out one of these. So same thing. You practice one of these in the homework. The inverse in this case. We need the 7th root. Burn through this. Y equals minus 2x to the 7th minus 1. Y plus 1 equals minus 2x to the 7th. Y plus 1 over negative 2 equals x to the 7th. Negative y minus 2, negative y minus 1 over 2 equals x to the 7th.
Wait, what if, oh, because we divided by a negative?
Yeah, just changing the signs. X equals the 7th root of negative y minus 1 over 2. The inverse is the 7th root of negative x minus 1 over 2. Answer these questions, all from the graph. Here we're just concerned about what they're asking for. Okay, so here, consider the function in the graph to the right. The function has a relative minimum of blank at x equals blank. So the definition of relative minimum is where you are locally the largest. That place is here. That is to say, in this area, about this area, this is the largest point on this graph, right? So from here to here, this is the largest point. And so that value is negative 3. And it occurs at 5. Similarly, this is the lowest point in some small area here. That point is negative 8, and it occurs at 0. Questions there? This function is increasing whenever it's going up. And so it starts increasing from, I should use a different color. It starts increasing from here to there. You track that by looking at the interval, the x interval over which that occurs. So it's only increasing over this interval, 0 to 5. Okay. It's decreasing from here to here, right? Right, and so that looks like it is coming from all the way back here, all the way up until here, till this point here, and then it starts decreasing from this point onward, right? So that looks like some minus infinity to 0 union with, is that 5?
Yeah.
5 to infinity. They ask the most obvious questions last for some reason. These are the questions you should answer first. That the domain looks like it's the whole rail line. Right, that this graph moves from left to right. What's the range? How far up and how far down? Same thing. These are questions where this is some x cubed thing. I'm gonna give this function in about a couple weeks. I'm gonna give this function to my calculus class without the graph. I'm gonna write f of x equals this. The graph will look like that, and they'll be able to answer all of those questions without looking at the graph. That's the challenge, right? And that's what, again, that's the brilliance of Newton, Leibniz, Weierstrass. There's something about that function and something about calculus that lets us answer this question without ever having to look at the graph. Oh yeah, so let them know. Oh wait, we're on 21. Let them know they have a lot of fun coming up, right? Solve the inequality. So this is the last few things we did. So if you look at your notes from the last class before we started to review, it's this stuff. I had mentioned that this one in particular was on the test. That again, you set the function equal to 0. Let's see if I copy it into that. Perfect. You set it equal to 0, and then you do a number line x minus 3 times x minus 5 squared equals 0. That happens when x is 3 and 5. Number line. 3, 5. We're talking about picking values and plugging them into x minus 3 times x minus 5 squared. And when x is 300, you get a positive. When x is 4, you get a positive. And when x is 2, you get a negative. We're looking for the negative because I want to get less than 0. So that's minus infinity to 3. They do not write this in integral notation. I'm just addicted to integral notation. But that's this one. What polynomial is that? Semi out of order. But we have the game plan for this now. We got some zeros. We've got an x plus 2. We've got an x minus 2. And we've got an x minus 3. What do we need?
X plus 2 needs to be even.
Squared. And then there's omega. And at 0, we need negative 4. We just figure it out like we did the other ones, right? So at 0, yeah, at 0 needs to be negative 4. And so we're talking about, if that's f of x, at negative 4, you're supposed to get omega times 2 squared times negative 2 times negative 3. Negative 4 equals omega 24 times 24. Omega is negative 1 over 6. That fits the form pretty nicely. Again, the degree of this is 4, right? 2 plus 1 plus 1, right? So, and the number in front is negative. The table makes it clear that when you have a polynomial of degree 4 and the number in front, if you have a polynomial of degree 4, it rises on both sides. right? If the coefficient is positive, but here the coefficient is negative, so it falls on both sides. The off the record remark is that it has 3 humps in this picture, and so that means the degree should be 1 more than that. Questions there? And then for the game, a rational inequality. Set the numerator equal to 0, set the denominator equal to 0, and then find where the negatives are. Number line, we got a -5, a 2, and a +5. Right, so x minus 2 equal to 0 gives x equals 2. X squared minus 25 equals 0 means x squared is 25, which means x is 5 or -5. Plugging in values into x minus 2 over x squared minus 25. 6 gives a positive. 3 gives a negative. 3 squared minus 25 is negative. 0 gives a positive. And -4 trillion gives a negative. Okay. We're looking for the negatives, so it's minus infinity to -5 union with 2 to 5. That is part 2. I'll take any questions about anything we talked about from questions 12 through 23. We'll stop the recording there. And then